Now, can you just picture this? Every single day on this planet, folks burn through over 9,900,000 barrels of oil. That's like what? 1 billion liters. Pretty wild to think about, right? But what is oil, really? How does this thick black goo actually get turned into the energy that powers our entire world? Today, we're gonna dive deep into the seriously fascinating world of oil production. We'll start with how it even forms over millions of years, then check out the incredible tech in modern wells that punch down tens of thousands of feet into the earth. We'll cover everything from those giant platforms way out in the middle of the ocean to the complex refining steps that take that raw material and turn it into clean fuel. Ready to find out the real story behind that black gold? Let's just jump in and see how natural gas really works. Folks are projecting that average oil production in the United States next year is going to hit right around 9,900,000 barrels per day. But honestly, do you even know what oil is or where it even came from in the first place? I mean, everybody talks about oil this, oil that, oil spills, oil production. But nobody ever really tells you what it actually is. Well, stick with us and we'll just break it down for you. The way oil forms is a seriously long-term project, taking millions of years. It kicks off with a bunch of organic stuff, like the leftovers from ancient plants and little critters, piling up on the bottom of old seas and lakes. Over time, these plant and animal remains get buried under layers of sedimentary rocks, things like clay and sand. Then, under a ton of pressure and heat, which gets way more intense the deeper you go, that organic material starts transforming into something called kerogen. It's kind of a solid, waxy material. If the temperature keeps cranking up, hitting somewhere between 140 and 302 degrees Fahrenheit, that kerogen breaks down using heat. And bam! You end up with liquid hydrocarbons. So, yeah, that's us your oil. If you didn't find that interesting, seriously, let us know what you think is cool. Just write it down. Okay, so the oil that formed just like we explained, it actually travels through porous rock until it runs into something called a trap. Think of that as a geological structure that just stops it from moving any further. It starts building up there, and bingo, you've got yourself an oil field. It's kind of fascinating that scientists are still having debates about the exact details of this whole process, and whether oil might form in other ways too, not just from ancient organic bits. People started pulling oil out of the ground way back in ancient times. But the real deal oil boom didn't kick off until the 19th century. That's when the kerosene lamp came along. To actually get your hands on the oil, the absolute first step is figuring out precisely where it's hiding. This phase, geological exploration, is easily one of the toughest and most expensive parts of the entire oil extraction game. Scientists aren't just walking around with shovels, you know? They're using satellite images, magnetometers, seismic waves, and other super high-tech methods. Seismic surveying is actually pretty spectacular to witness. They set off controlled underground explosions in a specific area, or use special vibrating platforms to create waves that travel down through the rock layers. These waves bounce off different layers in the ground and come back up, and sensors pick them up. It's like building a three-dimensional picture of what's underground, essentially letting them see beneath the surface. Once the geologists pinpoint a promising spot, the actual drilling kicks off. A rig, whether it's sitting on land or floating out in the ocean, turns into this giant humming machine that runs non-stop 24/7. The drill string, those are steel pipes with a cutting bit on the end, bores into the earth, spinning it up to 200 rotations per minute. To keep the drill bit cool, carry rock pieces out, and stop the hole from collapsing, they pump in drilling mud. That's a thick mixture, usually water or oil-based. Modern wells can go seriously deep, ranging from 10,000 feet down to 16,000 feet. And sometimes, way deeper, up to 35,000 or even 40,000 feet. For instance, over in places like Texas or Saudi Arabia, they're drilling wells that stretch over 26,000 feet long. And often, a big section of the well goes sideways, horizontally. This lets them tap into a much bigger chunk of the oil reservoir without having to drill a bunch more vertical wells. One of these operations can cost you anywhere from a few $1,000,000 to easily tens of millions of dollars. And honestly, it doesn't always work out successfully. But if the well does turn out to be a producer, oil starts making its way to the surface, either pushed by its own natural pressure or pulled up with pumps. And that's when the next big stage begins, actually getting the oil out, processing it, and shipping it off. Speaking of major producers, Saudi Arabia is right up there as one of the biggest oil producers globally. Just back in February, Saudi Arabia was pumping out nearly 9 million barrels of oil every single day. This country actually has a solid chance to boost its standing in the energy market even further, especially since Saudi Aramco recently announced they found 14 brand new oil and gas fields right there in the country. So, once all the exploration and well drilling is completely finished, the absolutely crucial stage begins, actually pulling that oil out of the ground. If the field is really rich, the oil itself might just start pushing its way up to the surface simply from its own pressure. That's what's traditionally called a gusher. And while it might look pretty dramatic, with those big streams of black liquid shooting up into the air, these days, that method is seen as pretty old school and kind of dangerous. Modern wells are outfitted with sophisticated systems of valves and regulators that allow them to precisely control the pressure and the volume of oil that's flowing out. The oil gets to the surface through a network of pipes, and then it heads over to what's known as a processing facility. That's where they separate it from other stuff that came up with it, like associated gas, water, sand, and whatever else is mixed in. This step often happens right there at the extraction site, either on those big platforms out in the ocean or at bases on land. Separating all those impurities is a pretty cool process to watch. The oil mixed with all the extra stuff goes into this large, sealed tank, and gravity gets to work inside. Gas is light, so it floats up to the top. They collect it through an upper outlet. Water is heavy, so it settles down to the bottom. They drain it off through a lower valve. Oil is in the middle in terms of density, so it hangs out between those two layers. Now, if tiny droplets of water get kind of stuck in the oil, it's not quite as simple to separate them out. That's when they might add something called demulsifiers. These are chemicals that break up that mixture. Or they might heat the oil up a bit, which also helps those different layers split apart. But hey, let's get back to the extraction itself. Sometimes, to increase the pressure down in the rock formation, they use what are called secondary recovery methods. For instance, they might pump water, gas, or even steam into other wells. This helps to kind of push the oil towards the well they're actually producing from. Technologies like this can help them pull out up to 60% of the oil reserves from a field, whereas without them, that number could be cut in half. The average amount of oil a modern well in the United States produces is anywhere from 500 to 1,500 barrels per day. Just think about that for a second. One barrel is 42 gallons. Now multiply that by the thousands of wells operating all over the planet. And that really gives you a sense of the true scale of oil extraction. Oil by itself is actually a really complex blend of hundreds of different hydrocarbons, ranging from those lighter gases all the way up to heavy fuel oils. To get gasoline out of it, that's that light, easily ignitable part that internal combustion engines can use effectively. The raw material goes through several technically tricky stages at an oil refinery. It all kicks off with something called fractional distillation. Crude oil is first heated up to temperatures between 660 and 750 degrees Fahrenheit and then fed into a distillation column. This is a tall tower where the temperature gets cooler as you go up. Different components of the oil vaporize and rise to different heights, where they cool down, turn back into liquid, and are collected at various points. The gasoline part, it's one of the lighter ones, is typically collected at levels corresponding to temperatures between 104 and 392 degrees Fahrenheit. But simply distilling the crude oil isn't quite enough to get high-quality gasoline. You only get about 15 or 20% of the gasoline fraction this way, and most of what comes out still has stuff you don't want in it, and an octane number that's just too low. To boost the total amount of gasoline they get, they use a process called cracking. This is basically all about breaking down those long hydrocarbon molecules into shorter ones. The most common way is catalytic cracking, where heavier parts are heated up to almost 1000 degrees Fahrenheit in the presence of catalysts. This lets them get extra gasoline from those heavier leftovers. Sometimes they also use hydrocracking, which involves hydrogen under high pressure. When it's all said and done, the percentage of gasoline you can get from just 1 ton of oil can reach 40 or 50%. That depends, of course, on the type of oil and how sophisticated the refinery is. The gasoline they get from these cracking steps usually has a low octane number, meaning it would cause knocking or detonate too early in an engine. To fix this, they put it through a process called reforming. This means rearranging the structure of the molecules at high temperatures, usually with platinum catalysts present. This really boosts the octane number, potentially all the way up to 98, making the fuel perfectly suitable for today's cars. In the very last step, they mix additives into the gasoline to improve how it works. This includes things for anti-corrosion, preventing engine knocking, cleaning the engine, and reducing environmental impact. This helps keep the engine healthy, cuts down on harmful stuff coming out of the tailpipe, and makes the fuel more efficient overall. Just one modern oil refinery can process up to 400,000 barrels of oil every single day. That's pretty impressive, especially when you stop and think that daily gasoline consumption in the United States is roughly 370 million gallons. Besides going to our homes, natural gas also gets sent to power plants, factories, and chemical facilities. For big industrial users, they need way higher pressure and volume. They're using pipes with diameters up to 48 inches and pressures up to 1,500 psi. Gas can even be turned into a liquid. They cool it way down and ship it in massive tankers across the oceans. Are you ready to peek into a world where millimeters decide life and gleaming metal travels a path from a piece of raw material to deadly precision? Imagine this. Over 12 billion rounds of ammunition are produced worldwide each year for the military, police, hunters, and athletes. And each one is the result of precision engineering, where temperature, pressure, and shape matter down to the last decimal place. In this video, we'll show you everything. From selecting gunpowder and alloys for the casing, to control tests where the muzzle velocity is almost 300,000 feet per second. Get ready. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the edge of what's possible. Hundreds of millions of bullets roll off factory assembly lines around the world every year, and each one passes through quality control lines with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive rolls about 0.06 inches thick and weighing up to 6,000 pounds. These rolls are supplied by metallurgical plants, most often in the United States. These are companies like Olin Brass or Chase Brass. The rolls arrive in sealed packaging to prevent oxidation during transport. Upon arrival at the factory, the brass is uncoiled on a special platform and fed into a rolling machine, a huge heated steel drum. The metal's temperature at this stage reaches 600 degrees Fahrenheit to make it more pliable. The brass is flattened. Any deviation means rejection. Next, the brass sheet is fed into a press line, a high-speed stamping press that, with lightning precision, punches out small discs, so-called blanks. Their diameter is approximately 0.75 inches, and their thickness matches the original sheet. The press operates at up to 250 strokes per minute, so every second yields a new batch of blanks. The resulting discs are heated to 800 degrees Fahrenheit. This is necessary for the subsequent deep drawing process. They are dipped in lubricant and fed into a hydraulic press, where, under pressure of up to 100 tons, the disc is formed into a primary casing, still without details, just a cylindrical shape. This process is repeated several times, each time drawing the casing a bit longer and thinner. At this stage, the blank already resembles a casing, but is still far from its final appearance. Each casing is annealed after drawing, This involves heating it to 1000 degrees Fahrenheit to relieve internal stress in the metal. Otherwise, the casing could crack during firing. Then, it's cooled in water and cleaned in an acid solution to remove scale and lubricant. Next, calibration and weighing. The casings pass through a high-precision laser control system. A weight discrepancy means automatic rejection. Length, wall thickness, cylindricity, and even acoustic response are similarly checked. Special sensors detect if a casing has microcracks or internal defects. Finally, the casing is trimmed to the exact length, a groove for the primer is cut, and the mouth is expanded to accept the bullet in the future. Then it either goes to the final assembly line or is packaged for separate sale. Casings are bought for sport shooting and military orders alike. The next critical stage is primer installation. This is a small but extremely important component that initiates the explosion. The primer is a miniature explosive device. Inside a metal cup is a primary detonator, usually based on lead styphnate or lead-free substitutes. Before installation, primers are checked for sensitivity. Those that react to a weaker impact or have an unstable explosive concentration are rejected. On an automated line, each casing passes through a priming station where, with incredible precision, a mechanism inserts the primer into the rear of the casing and crimps it so it doesn't fall out during recoil. Next, gunpowder. The type depends on the ammunition's purpose. For pistol rounds, most often spherical smokeless powder. For rifle rounds, extruded powder in the form of small tubes. On average, one .223 Remington round contains about 24 grains of powder. For comparison, a 45 ACP round contains only 5 or 7 grains. Gunpowder is measured automatically to the thousandth of a grain. Too much or too little is a danger to the shooter and the weapon. An error of 1/10 of a grain is unacceptable. Some systems use real-time optical scales that react even to vibrations in the workshop. Once the powder is loaded, it's time to seat the bullet. The bullet itself is another story. Material, shape, mass. Everything depends on the task. Hunting, military, sports, defense. But seating occurs with the same precision. The bullet is pressed under pressure into the casing, and then the mouth is crimped so it doesn't pop out during feeding into the barrel. After this, final calibration and visual inspection by eye through a camera with a neural network that manages to analyze each round in less than a second. The rejection rate is less than 0.3% at large enterprises. And only after all stages of inspection, calibration, and final weighing does the bullet reach the final phase: packaging. Packaging isn't just about aesthetics or ease of transport. It's a matter of protection, identification, and logistics. Because when you're shipping 50,000 rounds to a single client, mistakes are not forgiven. It all starts with counting. Bullets are automatically sorted into trays or fed onto weighing lines, where batches are formed in quantities of 20, 50, 100, or 1,000 pieces, depending on the customer's specifications. The cheapest packaging option is plastic trays with shrink wrap. This is a budget solution for the civilian market, convenient for shelves and mass sales. Military supplies are packaged differently, in zinc or steel containers with airtight lids. Inside, liners with anti-corrosion treatment, markings with caliber, lot number, manufacturing date, and QR codes. One such box holds from 1,200 to 1,500 bullets, with a total weight of up to 40 pounds. In some cases, containers with moisture control systems, or even built-in trackers for delivery monitoring. On industrial lines, one shift packages from 100,000 to 300,000 bullets. Some factories operate in 3 shifts, 24/7, especially during periods of high demand such as military contracts, crises, or elections in the United States. The productivity of one packaging machine is up to 12,000 units per hour. In workshops with gunpowder, primers, and explosives, there is anti-static flooring. This is a special coating that diverts electrostatic charge from a person's body or equipment to the ground to prevent sparks that could cause explosions or ignition of explosive substances. Also, the humidity in the workshop is maintained at 40 to 60%, which reduces the risk of dust or particle ignition. In areas with metal dust, oil vapors, and fumes from galvanizing, ventilation with filtration is mandatory. Workers wear special suits made of natural fabrics or anti-static materials. It is forbidden to wear metal objects, watches, jewelry, or phones. Only certified specialists are allowed in the gunpowder or primer areas. Access is strictly biometric. People do not touch gunpowder by hand. Everything is handled through sealed automated systems. Primer formation, explosive mixture dosing, casing sealing, all are maximally automated. Robots or shielded machines handle the most dangerous stages. Powder fire extinguishers, sprinkler systems, and special containers for isolating ignition are placed every 150 feet. Personnel undergo mandatory training every 3 or 6 months. Evacuation, firefighting, first aid. All casings, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they are disposed of or recycled. The factory is guarded like a high-security facility. Video surveillance, armed guards, inventory of every unit. In 1998, in the United States, a plant manufacturing gunpowder for sport ammunition exploded due to violations of storage rules. Several types of mixtures with different properties were stored nearby. The explosion's power was equivalent to several tons of TNT. 4 workers died. The investigation revealed dozens of systemic violations. Therefore, safety at such plants is more important than the product they manufacture. Imagine a material lighter than plastic, but 10 times stronger than steel. It's the stuff they use to make National Aeronautics and Space Administration rockets, high-performance race cars, and armor for fighter jets. But you know what the paradox is? This super material is almost impossible to recycle. Its production is mind-blowing. Scorching furnaces, molecular transformations, nanotubes, cold plasma. But what happens when these parts wear out or break? The world got hooked on carbon fiber, and now it doesn't quite know what to do with it. In this video, the whole truth about the strongest material of our time. Don't touch that dial. It's about to get even stronger. The production process for carbon fiber starts with getting the raw material, polymers, most often polyacrylonitrile. This polymer consists of long chains of molecules that undergo special processing to give them the necessary properties for later transformation into fiber. The first step is extrusion. The polymer is melted and forced through tiny holes, forming fibers about 3/millionths of an inch in diameter. These fibers are gathered into bundles, called tows, and prepared for the next stage, stabilization. Stabilization is a chemical process where the fibers are heated in the presence of oxygen at temperatures ranging from 400 degrees Fahrenheit to 600 degrees Fahrenheit. As a result, the polymer molecules change their structure, becoming more heat-resistant and ready for carbonization. The next and most crucial stage is carbonization. The fibers are heated in an oxygen-free environment to very high temperatures, from 200 to 500 degrees Fahrenheit. Under the influence of such temperatures, all the light elements like hydrogen, oxygen, and nitrogen evaporate from the fibers, leaving behind almost pure carbon. It's this process that gives the fibers their unique strength properties. After carbonization, the fibers might undergo additional treatment, such as applying a coating to improve adhesion with a composite matrix. The resulting carbon fibers are collected into fabrics or matrices of various structures. These can be unidirectional bundles, woven fabrics, rolls, and so on. The choice of structure depends on the final application and the required mechanical characteristics. Next, these fabrics are impregnated with special resins, epoxy, polyester, or others, which allows for the creation of a composite material, a carbon fiber reinforced polymer composite. This composite boasts high strength and rigidity while remaining lightweight. Lamination is the process of layering sheets of resin, impregnated carbon fiber fabric, into a mold, where under pressure and heat, the resin polymerizes and the material hardens. The result is a strong, lightweight, and durable part in the desired shape. Thanks to its unique combination of lightness and strength, carbon fiber has found wide application in many fields. In automotive manufacturing, it's used for making body panels, suspension parts, and interior elements. This significantly reduces the car's weight, improves dynamics, and lowers fuel consumption. In aviation, carbon composites are used in fuselages, wings, and other structural components of aircraft. This increases fuel efficiency and reduces carbon emissions. In the space industry, the material is used in the production of rocket bodies, satellite panels, and elements of space stations. Carbon fiber withstands the extreme conditions of space and has high durability. Bicycles, tennis rackets, skis, boats, and even sportswear are made from carbon fiber to enhance performance characteristics. And reinforcing concrete structures with carbon composites increases their strength and resistance to corrosion. This material offers high strength at low weight. After all, carbon fiber is 5 or even 10 times stronger than steel, but significantly lighter. The fiber has excellent resistance to corrosion and chemical attacks. It also boasts high stiffness and resistance to material fatigue. Plus, it allows for the formation of complex shapes and parts, and it has thermal stability and a low coefficient of thermal expansion. But the high cost of production limits the use of carbon fiber in mass manufacturing. Also, the material is brittle and can fail under strong point impacts. Undoubtedly, carbon fiber is difficult to repair and recycle, and its mass use is also hindered by the energy intensity of the carbonization process. Carbon fiber continues to evolve thanks to innovations in production technologies and new areas of application. New carbon fiber production technologies aim to increase efficiency, reduce energy consumption and material cost, and expand the raw material base. One of the most promising discoveries is the cold plasma pyrolysis method, developed by David L. Chandler at the Massachusetts Institute of Technology. This process uses ionized gas at room temperature to break down polymer fibers into carbon fibers. Such an approach significantly reduces energy consumption and harmful gas emissions compared to traditional high-temperature pyrolysis. Furthermore, research in the field of carbon nanotubes opens up new possibilities for creating fibers with improved mechanical and electrical properties. For example, a team of Chinese scientists developed double-walled carbon nanotube fibers using a dry jet wet spinning method, providing high electrical conductivity, up to 86% of copper's conductivity, tensile strength, and high toughness. These fibers demonstrate durability even after 5,000 bending cycles, making them promising for the aerospace industry and energy storage. Other innovations include the use of computer modeling and simulations to predict the properties of new materials and accelerate development. The company 3M, for example, uses ultraviolet, electron beam, and laser irradiation to create high-precision structured materials that enhance the strength and stiffness of carbon fiber-based composites. Developments are also underway for new technologies to reduce cost and improve the environmental friendliness of production, particularly using waste from the pulp industry as raw material, which reduces industrial waste and makes the process more sustainable. In the future, further improvements in production technologies are expected, along with the emergence of hybrid composites with nanomaterials and the expansion of carbon fiber applications, from transportation and construction to energy and electronics. Recycling carbon fiber is currently a complex and important process, as this material is widely used in high-tech industries, but its waste is difficult to process due to the complex structure of composites. There are several main methods for recycling and reprocessing carbon fiber reinforced composites. Mechanical recycling involves shredding the waste and separating it into resin particles and short carbon fibers. The short fibers are used as filler in construction or for manufacturing plastics. This method is simple and environmentally friendly, but it damages the fibers, reducing their strength. There's also high-temperature pyrolysis. Waste is heated to 200,000 degrees Fahrenheit in an inert atmosphere. The resin decomposes into pyrolysis products, and the fibers are recovered. The process requires precise oxygen control to avoid damaging the fibers. There is also a fluidized bed option, where the resin decomposes in a stream of hot air, and the fibers are separated by a cyclone separator. Microwave-assisted pyrolysis involves irradiating the waste with microwaves, which accelerates resin decomposition. The method is simple and effective, requiring less equipment. Chemical recycling, or solvolysis, involves dissolving the resin in special solvents, such as nitric acid with alcohol or supercritical fluids, allowing the fibers to be separated without damage. The fibers retain their length and strength, but the method is expensive and currently mostly laboratory-based. Other recycling methods for this fiber include radiation exposure to break down the matrix, ultrasonic treatment, and the development of new chemical reagents to separate the composite components. As you can see, the bigger challenges right now lie not in producing the material, but in recycling it. Recycling carbon fiber is crucial for reducing the environmental burden, as composite waste does not decompose naturally and takes up significant space in landfills. Modern technologies allow for the recovery of secondary fiber, which can be used in construction, plastics production, and even for reinforcing concrete structures. Did you know that your old air conditioner could poison the soil, wreck the ozone layer, and even cost you thousands of dollars in fines? Every single year, Americans throw out millions of air conditioners, and each one is a ticking time bomb of toxic chemicals, heavy metals, and dangerous gases. In this video, I'm going to show you how they actually get recycled. Freon, copper, mercury, nothing gets spared. And trust me, this affects all of us. So first things first, why should anyone bother recycling an air conditioner the right way? To answer that, let's break down what's actually inside one of these machines. Air conditioners contain refrigerants. These are chemicals that can do serious damage to the atmosphere. Older units use ones that destroy the ozone layer. Newer ones, they may not harm the ozone, but they still contribute to global warming. The internal boards and compressors are loaded with toxic stuff like lead, mercury, and cadmium. If you just dump an old AC in a landfill, all that junk can leak out into the ground and water. Now, compressors also contain valuable metals like copper, aluminum, and steel. Those can be reused, cutting down the need to mine more raw materials. But here's the kicker. If you try to tear one of these apart without the right safety measures, those toxic materials can leak out, fast. That's why so many countries, including the United States, have strict environmental laws banning improper disposal. And yeah, in some cases, those fines are no joke. In the United States, old air conditioner disposal is regulated on a federal level by the Environmental Protection Agency, plus individual state rules on top of that. Now, we've already touched on how long these machines usually last. So let's dive deeper. Window and portable units typically last from 8 to 10 years. Split systems? They give you a few more. And those big centralized setups, yeah, the ones we mentioned earlier, they'll run for about 15 to 20 years. Keeping filters clean, topping off refrigerants, and doing regular checkups can stretch that lifespan. But in hot areas where ACs run all summer long, they tend to wear out faster. Once your system hits the end of its life, it loses efficiency. Your power bill goes up and repairs become a money pit. That's why most people end up replacing them, which means more units headed for recycling. There are several ways to recycle air conditioners in the US. A bunch of utility companies run take-back programs for old ACs. Some even offer cash, anywhere from $25 to $100, just for handing your unit over. All you gotta do is apply, and a technician comes out to pick it up and handle it properly. Big chains like Best Buy, Home Depot, and Lowe's will take your old AC for recycling too. Some states have dedicated drop-off sites for electronic waste where you can bring in your unit for free or a small fee. In many cities, there are special bulky item collection days. And some towns offer curbside pickup of old appliances, sometimes even for free if you book ahead. Even charities like Habitat for Humanity Restore take working ACs to resell or use in community programs. And a lot of stores have trade-in deals, where you bring your old one in and get a discount on a new model. When we're talking about centralized systems though, you can't just yank one out yourself. You need to call a licensed tech. They'll recover the leftover refrigerant using special equipment, then ship the whole system off for proper disposal. In many states, improper disposal can mean fines, from $100 to $500 on average. But in some cases, it can climb into the thousands. Bottom line, either take your unit to a recycling facility or use one of those special programs. That's the smart move. Once the AC arrives at the facility, the first step is a professional teardown to safely remove hazardous materials and prep everything for recycling. Removing Freon is a whole process that needs special tools designed to safely extract it from the system. The technician hooks up a refrigerant recovery machine to the AC's tubing system. This device uses vacuum pumps and pressure gauges to control the flow. The system gets opened through service valves, giving access to the Freon lines. The vacuum pump slowly pulls the refrigerant out and transfers it into a sealed recovery cylinder. The tech keeps an eye on the gauges to monitor pressure and make sure every last drop is extracted. Depending on the unit size and how much refrigerant is inside, this process can take anywhere from a few minutes to half an hour. During this step, the workers are fully suited up because contact with refrigerants can be harmful. The equipment's built to prevent any leaks. Everything happens in a sealed environment. Once the Freon is removed, it's stored in that sealed tank and later handed off to certified hazardous waste recyclers. With the refrigerant safely gone, the unit moves on to the disassembly phase, which is crucial for proper recycling. The techs set up special workstations at the facility. Before disassembly starts, they review the paperwork and lay out a plan so they know exactly which parts to pull and how to sort them. The AC gets broken down into its core parts: the outer casing, compressor, heat exchanger, fan, electronics, piping, and smaller components. A typical unit has around 20 to 30 different pieces. The compressor alone might weigh between 30 and 50 pounds. Radiators, anywhere from 20 to 40 pounds each. They use both hand tools and machines, like hydraulic lifts and electric grinders, to cut or unbolt the big metal parts. This step takes about 30 minutes to 2 hours per unit, depending on size and complexity. Once everything's apart, the pieces are sorted by material: metal, plastic, and electronics. Around 90% of the metal in an old AC can be recycled. Metal gets cleaned of paint and grease, then sent for smelting and reuse. Plastics go to specialized recycling plants. Electronics that contain dangerous stuff, like lead and cadmium, are sent to e-waste recycling centers. On average, just one unit can provide 5 to 15 pounds of recyclable metal. That's a big deal when it comes to saving raw resources. Many recycling centers handle tens of thousands of air conditioners every year. That keeps a massive amount of toxic waste out of landfills. After the unit's fully disassembled, the next key step is sorting and prepping the materials for reuse. This process helps maximize resource recovery and shrink the environmental impact. After the initial cleaning, materials are sorted by quality standards. Metals get split into categories: aluminum alloys, steel, and copper. For example, copper wiring is often separated because its market value sits around $4 to $5 per pound. Plastic waste is grouped by type. The bundles for recycling usually weigh between 5 and 20 pounds. Electronic components are sorted by type: motherboards, capacitors, batteries. So recyclers know which ones need special handling, especially those containing rare metals. After sorting, all materials are packed up for transport. Metal parts go into containers headed for smelters. A single container can hold anywhere from 500 to 1,000 pounds of metal. Plastic granules are bagged or boxed up, usually in 50 to 100 pound batches, ideal for manufacturing. Electronics are shipped to specialized facilities where they get broken down even further. Thanks to this whole process, a single air conditioner can yield a surprising amount of reusable material. Recycling and disposing of A to C the right way also saves energy. Smelting recycled metal takes about 60% less energy than making new metal from raw ore. And today, some companies are already rolling out tech to automate disassembly and sorting, making the whole system more efficient and less dependent on human labor.